Okay, we'll get started now. Okay, so today we're going to go over the first lecture. So this will be for the first experiment that we're going to do online. And I'll have more details on that, not today, but I'll probably send an email out before our next class to kind of give you an idea or a heads up of how we're actually going to do the lab virtually. So I think I mentioned last time that we don't actually have any software to do the lab virtually like some schools do. They only do that. They don't have labs in person. But we don't have that software, so we're going to rely on VKS, which I showed you guys last time. And we're going to look at that a bit more today too for part of the lecture, so I can explain some things, visually, so you can actually see what it would look like in person. So yeah, we're going to use VKS for the experiments, and then we'll also use probably like some YouTube videos that I find that go over the experiment as well. And for this lab, I'll have to find the video, but I have a video when I took this lab myself to kind of show you what it would look like if you actually did the lab in person, because it is a pretty cool lab. We're breaking these metal rods apart from tension. So before we get started with the lecture, I want to go over some stuff on Canvas that I don't think I went over last time. Okay, so let me do that. So right now I'm on the home page for our Canvas, site. It's for this class. So again, I think some of you are new. You weren't in the class last time, so in case you guys haven't used Canvas before, we're on the home page for, the school's website. I'm going to click over here on the left-hand side for Canvas. That'll take us to the dashboard. Then I click on EGME 36A for this class. Then we're on the home page. So I'm going to click on, actually first I want to show you guys files. If you go on the left hand side, I'm going to go to student view. If you go on the left hand side here, you'll see that there's a link for files. So if we click on that, you can see that I have these folders here. So I have course materials. I think I have the syllabus in there. Yeah. And lab handouts and lectures. So this is like a more centralized area or a place on our course site where you can access the lab handouts that we have for each lab. Just so you know, I don't write these; they're from the department. So if it sucks, it's not my fault. They are pretty good though, and I'll show you what that looks like in a second too. And then we have a folder for lectures. So here I'm going to I'll post the lecture notes that I write in class with you guys. And if I ever make slides too, I'll put them here. So there's some of my classes I actually make slides and I go over or write stuff down in class as well. But I didn't make any slides for this lecture today. I think it's just better to entirely write everything on my iPad. So I'm going to go back to the home page. And if we click on today, it'll take us to today's page. So here we have the schedule. So we're going to talk about stress and strain. That's the main part of this lab. We'll talk about the stress strain diagram, engineering stress, the elastic modulus, ductility, and then Hooke's law. So, I taught this lab 2 times before, 2 different semesters. And I think this first lecture is actually one of the longer ones that we have. It's not super long, so don't worry. But some of these lectures, they go by, super fast because we'll talk about, stuff in the lecture, but the main emphasis is usually on the lab. So being virtual is kind of a bummer here. But yeah, so basically the point is this lecture is going to be longer than most, but they're all pretty short. So I'm going to click on this experiment handout. And you can take a look at this. It's mostly beneficial for if we were actually doing this in person again. I'm going to open it up in Firefox here. Oh, nope, it looks terrible. It looks all weird. It's because of my browser. I don't know why it looks weird, but if you open it up in your browser, it should look okay. So anyways, this is what all of the handouts, they usually look like. They'll have some theory on the handout itself, and then they'll talk about the procedure that you would look at if we were doing the labs in person. So this is the machine that we use for almost every lab. And I'll actually talk about this a bit today as well for the lecture. This is what we'd be using for the first lab. This is called an extensometer. We'll discuss that. But basically, you know, this has the entire procedure here, and that's it. And some theory in the beginning. But I'll always post these before our lectures, and it's not as much, you know, of use this semester, but it's there if you want to take a look at it. Okay, any questions before we get started today for the lecture? Alright, so I'm going to pull up my iPad here. I'm going to share my screen. Alright, let me stop sharing on here. Don't want to forget. Okay, so this is how I'm going to kind of do our lectures here. So I'm going to share my screen for my iPad, and you guys can follow along and take notes if you want. You don't really have to, you know, it's up to you, but I'll be writing stuff out on my iPad, and again, I can upload these notes as well to Canvas if you guys want. I'm going to change this really quick. Oh, also on Canvas, I forgot to mention, on the page for each day that we have for our meetings, I'll also post the video for our lecture there as well. So I think I already posted that for, you know, in the first week, I posted the lecture there as well. But for today, once we're done and the video is done processing on YouTube, I'll put the link for today's lecture on today's class page. Okay, so let's get started. The screen, it doesn't look like super high res, at least to me, but I haven't been able to find a better way to share my iPad screen at a higher resolution. I think this looks like 720p or something. Looks pretty bad, but it's not terrible. But I always try to get the best looking quality if I can. But you can read everything, you know, fine. So this is how it's going to be. Okay, so the first lab is going to be on stress and strain. So I think I mentioned it a few times, but I'll repeat myself again. So the first lab, we're going to have 3 different metal bars that we're going to put in tension. So we have an aluminum metal bar and 2 different types of steel. So we take these metal bars, we put them in that machine that we just saw, and we pull them apart in tension until we break them. And looking at these three different metal bars, we would look at the load data that we have and the deformation data, which we'll discuss today. And then we would convert that into a stress strain diagram so we can better compare the material properties of these 3 different metals. So I'll actually, I'm going to stop sharing my iPad really quick. I just want to give you some visual context here. So let me share my computer screen. I'm going to go to the VKS website here, and I'll click on the experiment. Wow, that was really loud. Okay. Okay, so this metal bar here, this is aluminum. Actually, no, it's not aluminum. It's 1018 steel. So the different bars, they are color-coded for the lab. So blue here, that's for 1018 steel. This is what the specimen looks like. And we would put it in this machine here. So we have these 2 jaws. So we'd put one end down here and the other end in this one and this jaw. And basically, this top jaw would move up and it would then put the metal bar that we have in tension. And we would keep on pulling it apart, until it breaks. So let's see if there's a an image of it broken. Also, we'd be using this, which again I'll talk about a bit later in our lecture. Let's go to the end, see if there's a picture when it's broken. Oh, I just saw one. Okay, yeah, so here it's broken. It makes a really loud noise in person when it breaks, but this is what it would look like. And you can kind of see in this picture that in this area here, the cross-sectional area is smaller than this area down here. And that's because of necking, which we'll talk about today as well. So this is what the experiment looks like in person. So I just want to give you some visual context before we actually get started with the lecture. Okay, so let's go back to the iPad. Are any questions on anything I just showed you? Okay. Okay. So let's go down. I have my notes I'm pulling up here. So the first thing we'll talk about is stress. Okay, so if you guys have already taken 331 Strength of Materials, or, I think they might have changed the name of that class, I forget, but it's basically Strength of Materials, Behavior Materials, Stress Mechanics, I don't know. There's a lot of names for it. But if you've taken the class before, a lot of this will be review, or if you're taking it now, you might have just gone over some of these topics in the first week of school. Okay, so stress is going to be the intensity of an internal force on some object. So we'll write that down and then we'll go over the actual mathematical equation. Okay, so we have the intensity, and I'm going to underline intensity of an internal force on an object. Okay, and then mathematically, stress, that's going to be given a Greek symbol of sigma. So we have sigma, that's stress, equals F over A. So F, that's going to be our force. Area, that's going to be the cross-sectional area. So I'll note this as well. We have sigma, that equals stress. F, that's going to be the force. You might see force, instead of being an F, you might see as a P. Same kind of thing. That's going to be the force or the load, whatever term you want to use. And then A is our cross-sectional area. Okay, and then as for units, our load, that'll be in pounds, or something like newtons, but in the actual experiment, I think by default, the equipment, it uses US units, so it'd be like pounds. Okay, and then for stress, we have pounds per square inch, or PSI. So I'll write it like pounds per square inch, or PSI. And then for the cross-sectional area, we have inches squared, of course. Okay, so, pretty simple, but I want to get the mathematical equation down. Okay, and then for our lab, what we have is, this will be put under axial loading. So axial loading is going to be along the longitudinal axis of our object. So I'm going to pretend that this is a kind of cylinder. So this would be our test specimen. Let me move this graph down. I kind of made this for later. Okay, so this rectangle, this is going to be our test specimen that we have. And we're going to have some loading on it. So in this case, we have loading on both ends. It's along the longitudinal axis of our object, and it's in tension. So this is what, it's going to look like for the experiment. Okay, so just one quick thing too, if I was to increase the force, then of course I'm going to increase the stress. We can see that from our equation that we wrote. And if I increase the cross-sectional area, if I wanted to have that same stress, I would then have to increase the force. So we'll kind of talk about this a little bit later on as well. Okay, so strain. So stress, really simple. And then strain, that'll also be pretty simple, but it's going to be the main kind of fundamentals that make up our stress-strain diagram that we're going to focus on for this lab. Okay, so we have strain. So just like I wrote for stress up here, stress was the intensity of an internal force. Deformation is going to be the intensity of our deformation. Did I say deformation twice? Strain is the intensity of the deformation. Okay, so deformation is, something that has deformed. So usually I show like an eraser and I would like pull it apart, but I don't know, I guess I can show you these like sticky notes, right? I can deform them by bending them. You can't really see it too well, but I can deform it, right? I can bend it however way I want. And also, once I bend this and then I release the force, it can go back to the position that I had it. So we'll talk about that in a bit too. That's because this is still in its elastic range. So I can deform it, and then I can go back to the original position. Okay. And again, this strain that we just saw, that was the intensity of however much I just deformed those sticky notes. Okay, and then strain, it can occur from a change in temperature or a change in stress. So for this experiment, it'll be from a change in stress or other phenomena like grain growth or shrinkage. So for the first experiment, it's going to occur from a change in stress. And for later on in the class, we'll have strain that's occurring from a change in temperature. So at least that'll be kind of part of it. That'll be in lab 5 for the Charpy impact. So in that lab, we have this like pendulum, and you just like, you drop this pendulum down and you strike some object and you break it. So that's an also pretty cool lab, but I feel bad for you guys because you can't do this lab in person. Other labs, it's not a huge deal that you can't do in person, but this is a pretty good lab for in person. Maybe I'm making it worse by saying that. Okay, so that's strain. We'll go over the equation as well. Okay, so I'm going to focus on normal strain, which, it's similar to other kinds of strain, but I'm going to be explicit in saying normal strain because we have this longitudinal tension for our beam. So it's along the longitudinal axis. Okay, so let's do normal strain. I'll write it out in words first. Maybe I should have done that for stress as well. So we have normal strain. That's going to be the deformation over the initial length of our object. Okay, and then I'm going to rewrite this in actual kind of mathematical terms here. So strain is going to be denoted by an epsilon. And then we have deformation, that's a delta. And then our initial length is going to be L sub IN just standing for initial. Or we can write this as epsilon. So strain is equal to delta L over L-IN. So delta L, that's going to be our change in length. I think the second way I wrote it is a better way to kind of understand it. So we have epsilon, that's strain, delta L, change in length, then L-IN, L sub IN, initial length. Okay, so either you already know this, or you might be able to tell that our units here are both, units of length. So for this class, it'll be like inch per inch. So delta L, that's, inches, and initial length, that's inches. So our units for strain are technically unitless because those units are going to cancel out. But we still write them as inch per inch or meters per meters, whatever unit of measurement that you are using. Also, sometimes the units might be in microstrain as well, which I don't think we're using that for this lab, but that would be just, times 10 to the minus 6. So for this lab, I think for, lab 1 and lab 2, the units that you're going to have for the data that I give you is in inch per inch. Might be wrong on that, but I'm pretty sure. Okay, any questions so far? Okay. So, scrolling down here, let's see. Okay. I'm going to talk about one more thing, going back to VKS actually. And that'll be talking about the extensometer. So I'm going to stop sharing here. Go to my desktop. Okay, so this tool that you see right here, this is called an extensometer. And this initial length that we have for the extensometer is 2 inches. Let's see if there's a better picture of it. Yeah, right here. So this initial length here is 2 inches. So once we put it on the actual specimen, this clamps on, and this length again is 2 inches, and that's known as the gauge length. And once we start applying tension to each of these metal bars, this extensometer, it will deform at the same exact rate as our bar over here. So you see the way it's designed, it can actually expand on the wrong way. So it can expand like that. So it's going to deform at the same rate as the metal bar. And this extensometer, we hook it up to the computer, so you can't really tell that well in this picture. This is a better picture here. So this cable, it hooks up to the machine, which then goes to the computer, and that will give us our deformation data. So again, it starts at a gauge length of 2 inches, but that'll be our initial length, and then we'll get the deformation data as it deforms and deforms and deforms at the same rate as the metal bar that we're deforming for the experiment. So that's how we get our deformation data in the experiment. So we get whatever the change in length is, divide that by 2 inches, which is the gauge length, and we would get the strain for the experiment. Okay, and then the load, we get loading data as well. The machine here in the background, that gives us load data that goes to the computer. And then we convert that to stress by just taking the load and dividing it by the cross-sectional area of the specimen. So we would divide it by this area in the middle here. So these end points here, they're where we attach that to the jaws for the machine. So if you're doing the actual lab, you would measure this cross-sectional area. Okay, let's go back to the iPad. Alright, so now we're going to talk about the stress strain diagram, which is, I guess, kind of the main, event for today's lecture. So we have the kind of preliminary stress and strain out of the way, so now we can actually go to the stress strain diagram, which we'll be kind of focusing on for the experiment deliverables as well. So before we start pointing stuff out on the graph or the diagram, we'll talk about what a stress strain diagram even is. Okay, so this is going to be a diagram that we generate by taking our load data and our elongation data or deformation from a tension test, and then we would convert that mathematically to stress and strain data. So take load and deformation data, and then we're going to convert that to stress and strain. Okay, so why would we do that if we already have the load data and we already have the deformation data? Why are we converting it to stress and strain? Which would be a good question. We're doing that because if we convert this to stress and strain, we can look at material properties kind of as a whole. So if it's just load data and deformation data, that data is only specific to that specific specimen that we tested. But if we convert that to stress and strain data, then we can convert different materials on that basis. So it wouldn't matter if I was, looking at an aluminum bar that was 2 inches long or an aluminum bar that was 4 inches long. If I run this test and I convert it to stress and strain data, those results that I get for our stress and strain graph to calculate some material properties, theoretically it should be the exact same, but in reality there's going to be a very slight difference. But, essentially they're going to be the same results. So by doing that conversion, we can compare materials on that basis and not a specimen only basis. Okay, does that make sense, or any questions on that? Okay, so I'll say conversion allows for insight on materials in general. And I'll underline materials just so we know that it's for the material and not for each unique specimen. Okay, so that's why we have that conversion. And once we have that conversion, we can plot stress and strain on a graph, and then we can get some more insight on that material. Okay. So I don't know if you're taking the class now, I don't know if you'll have got to this yet. That might be, or this might be a point of topic for this current week. So I guess you'll get a little sneak peek now if you haven't had your class yet. Okay, so the first thing that we have, I kind of, use different colors here to kind of indicate different regions that we have in this graph. So in this blue portion here, this is going to be our elastic range. Let me just draw that line. So everywhere in this blue line, I guess I can even kind of fill it in like that. This is going to be our elastic range or elastic region. So in blue, I'll put elastic region. Okay, so within this region, everything here, our material is going to behave elastically. So remember I had my, sorry, let me pull up my zoom here. Okay, so remember I had my sticky notes, right? And so here they're just in its relaxed kind of equilibrium state. And if I apply a load on it, I can bend it, so I'm deforming it. But if I release this load, it'll go back to its original position. So it's able to do that because the sticky notes, they were within their elastic range. At some point, if I apply too high of a load, I won't be able to go back to this original position. So this area in blue, that's that region that I was just showing you with the sticky notes. So it's the elastic region. So I can go all the way up to this very top point here. And if I release the load that I have applied on some object, all of that deformation or all of that strain is going to be recovered. Okay, so that's the elastic region right there. And we'll actually talk about this point up here. This very top point is going to be called the proportional limit. So I'll put a little label. Okay, so we can go up to this proportional limit, and then we can release our load, and we can recover all of that strain that was just applied on that object. So remember, strain is the intensity of the deformation that we just had on some object. Okay. And we'll put a little definition down here as well for the proportional limit. Okay, so this is going to be when our stress-strain relationship ends its linear relationship. So I'll say point where linear relationship stops. Okay, so let me zoom in, and you'll see that right after this point, our graph is no longer, this linear straight line. It starts to curve a bit. Okay, and we'll talk about the significance of that as well later on once we get to the elastic modulus. Sorry if you can hear my computer in the background, my laptop. I have a MacBook, and the fans on that are insanely loud. Okay, so that's the proportional limit. And again, just remember that if we go up to this point and we then release the load, we can recover all of that strain that we just had on some object. Okay, so we have another term here, which is going to be the elastic limit. Okay, so the elastic limit for most materials, it's basically going to be the same as the proportional limit. So they're going to be basically like right on top of each other. So I'll just draw a point right here. So the elastic limit, that's going to be the point where I can still go up to this elastic limit, and then I can release all of the load and all of the strain is recovered. So that's what I just said for the proportional limit. But again, for most materials, they're basically going to be the same point. For some materials, the elastic limit can even be, like out here, let's say. So we can still see that there actually is this non-linear relationship after the proportional limit and before the elastic limit. But for some of these materials, I could still release the load at the elastic limit, and I could recover all of that strain. Now for our class, that's actually not going to happen, so I'm not going to talk about this too much, but it's something that you want to keep in mind, that even though, in this case, what I have drawn right now, even though we're no longer in this kind of linear relationship for stress and strain, I can still release the load at this elastic limit, at this point in purple, and I could recover all of the strain. But what I'll do for our class, I'm going to put this down here. Because again, for our materials that we're going to be looking at for this class, the proportional limit and the elastic limit are basically going to be on top of each other. Okay. So let's go down here and we'll write its definition. So I'll say point where strain can still be recovered. Okay, and then anything after this is going to enter the plastic range. And we'll talk about that for yielding, which we'll talk about right now. So for yielding, let's see, I'll use, I guess, green. Okay, so yielding is going to occur after our elastic limit, which we see in purple. And yielding is going to be when we have a very slight increase in stress, or even sometimes none, and we have a very large increase in strain. So if you see after our elastic limit, on the left hand side we have our stress. So our stress is hardly increasing at all in this figure that I drew, but our strain is increasing a really large amount. So all in here in green. Yeah, it's fine. So let me just, it's bothering me. Let me move this down. Okay, so this is when we're yielding. Okay. So we have that very, very small increase in stress, but our strain has increased quite a large amount. So in this region here, this is when we have yielding. Once we go into this region, and let's say that we were right here on our graph, if I was going to release the load here, I can no longer recover all of the strain that we have. So in this region, I'm in the plastic region, which means that I can't recover all of that strain. So our object at this point is going to be permanently deformed to some amount. Okay. So for yielding, we're going to have a few kind of definitions here. So I'll say slight increase in stress, and then a large increase in strain. Okay, and then we'll say that this begins permanent deformation. Permanent deformation begins. Okay, so let's go back to our graph here, and then I'll draw, or I'll point out where this yield point is. So this yield point, it's also going to be very close to our elastic limit, because like we said, right after the elastic limit is when we start to yield. So this point in green is going to be denoted sigma y, which is going to be, which stands for the yield point. So that's the point when we start to yield. Okay, now let's talk about yield strength. So just to give you guys like a heads up, what we still have to talk about. We have yield strength, so we're going to talk about that now. And we have strain hardening, necking, fracture, elastic modulus, and then ductility. So we have a little bit more, but it's not too bad. I know if you've taken this class already, it's it's a lot of review, but all of this stuff, this is what we're going to be kind of going over in the lab. Okay, so yield strength. Yield strength, what color should I use? I'll use red. Okay, so for some metals, and we're going to actually see this for the lab for, I know aluminum for sure, and I actually think one of the steels that we have for the lab, we're going to run into this issue where we're not going to yield at a constant stress after the elastic range. So basically, it's going to be hard to see where our yield point begins. So to show you what this looks like, we're going to have something that looks like this. So this is our stress strain curve right here. So in our elastic range, let's draw this a little bit better. Okay, there. So pretend that I actually drew a nice linear line. So we have our elastic range, which needs to be linear. But in this graph here that I just drew, it's really hard to see when it stops being a linear relationship. So at some point we have our proportional limit, which is when we are entirely linear up to that point. So I'm going to say PL for proportional limit. And then after that proportional limit, we start to yield, but it's not really clear when this when this linear relationship stops here. So, in reality, we might have our yield point up here, or it might be down here. It's kind of hard to tell from this graph, because, it very kind of subtly transitions from a linear relationship to non-linear. So some materials, they're going to have a very defined yield point. So some of them, they might look something like this. So that's going to be, a very defined yield point here, and, it might do something like that. So in this case, we know that the proportional limit and the yield point, that they're, almost right on top of each other, because we have this linear relationship, and then it stops, and it goes non-linear right here. But for cases like what we have on the screen right now, it's not very clear, so to kind of deal with this, we're going to use something called a yield strength. Okay, so yield strength is going to be where we mathematically kind of defined a substitute for a yield point. Okay, so let's write down the definition. So yield strength, this is going to be when a specific amount of permanent set, that's the term that we use, for the strain has taken place. So when an amount of permanent set Okay, so permanent set, let me put for strain. That's going to be when we have a specific amount of strain, basically. So if we have our stress strain graph, we're going to look along our strain axis, And we're going to kind of mark off a point for some specific amount of strain. So typically this is given in either percentage or in inches per inch or meters per meter, whatever you're using. And it's either 0.05% or 0.2%. So that would be 0.0005 inches per inch or 0.002 inches per inch. So typically we use 0.002 inches per inch. So we might see something like this over here. Let's say at this mark here, that this is 0.002 inches per inch. So this is kind of a standard amount of strain that we use to define a yield strength if it's hard to determine where the yield point is. Okay, so how would this actually look, on a graph here? Okay, so pretend that that's our stress strain graph. So in this case, it's kind of hard to tell where our yield point actually occurs. So we're going to use this method to define a yield strength point. So what we do is we go to 0.002 inches per inch for our strain. And then what we have to do is draw a line that's parallel to the slope of our elastic range. Okay, so let's actually do it this way. I'm going to go over here. Okay, so what I just did, on my iPad, of course, is I just copied the exact slope for our elastic range. And what I'm going to do is draw it from the point where our yield point or yield strength starts to occur. So again, that's when we have a permanent set of 0.002 inches per inch. So what we have to do is start from there and then draw a line that's parallel to the elastic region. And at the point that it intersects our stress strain graph, that's going to be our yield strength. So at this point right here, this is our yield strength. Okay, so you want to make sure that you say yield strength and not the yield point, because technically they are different, because we're using this permanent set method for the yield strength when the yield point isn't easily defined in our graph. Okay, so any question on that? This is something that we're going to be doing for the lab. I know for aluminum, and I think there is another material too, where it's it's hard to find the yield point. So because of that, we're going to use this yield strength method. And I'll be going over how to do this in MATLAB with you as well. Okay. Alright, next thing is strain hardening. So I'm not going to spend too much time on strain hardening because it's not a huge kind of point of interest for this lab. But we have strain hardening in this region here in pink. So on this region right here. Actually, let's be a little more specific about this. It's going to be in this region in pink. So it's going to go up to our ultimate tensile strength, which I'll also talk about in a second. So we have strain hardening. Okay. Okay, so basically strain hardening is going to occur once yielding has ended. So you see in green here, our yielding has ended, so strain hardening begins. So basically this is when our specimen that we're testing can start to support an increased amount of stress. So once we're yielding, we have a very, very small amount of increase in stress, but we have a very large increase in strain. But at some point, we can start to support an increase in stress once again. And once we can start to support that increase in stress, that's known as strain hardening. Okay, so we will start to see our stress increase on the graph, which we see. And then at some point, it's going to kind of plateau. And at that point, once it plateaus, the curve is going to start to go back down. And eventually, we're going to reach a fracture point. So at this point up top here, I don't know, light blue, sure. So at this point here, this is our ultimate tensile strength, or UTS. You might hear different terms for it as well, but I'm usually going to call it the ultimate tensile strength in this class. Okay, and I'm going to write UTS for short. So at this point, this is the maximum amount of stress that our material can handle. Okay, so at this point, it's the maximum amount of stress, and then we're going to go back down for the amount of stress that we are currently taking. And then we're going to fracture at the end. So down here, we're going to fracture. And in between this ultimate tensile strength and fracture, we have a region called the necking. So let's use purple. So in this region here, we have necking that occurs. So I know I just kind of said a lot of things at once, but I want to focus on the UTS, necking, and fracture. So after strain hardening, we're going to reach a point where our stress, during strain hardening, our stress is increasing, it's increasing. And then we reach a point where it starts to plateau out and it goes back down. So at our maximum point, that's our ultimate tensile strength, or that's the maximum amount of stress that our material can handle. Now, after this UTS point, the stress starts to decrease because we have necking that's occurring in our material. So to show you what this looks like, okay, so let's say that this is our material that we're testing. Pretend it's a cylinder. So we're pulling this apart in tension, and at some point as we continue to pull it apart, our cross-sectional area, it has to change because we're deforming this material. We're making it longer. We have deformation, so our material is kind of stretching out because it's in tension. So when this occurs, it's going to be a terrible drawing, but just go with it. I'm going to exaggerate it here. Okay, so, yeah, great drawing. So we're pulling it apart. This should actually also be longer, so I'm just going to make this smaller. Yeah. So this area here is necking. So there's going to be this area towards the center of our specimen where the cross-sectional area is getting smaller and smaller, and that's occurring because our specimen that we have is deforming, or it's getting longer in length. Okay, so it's going to be this kind of localized area, and I should also actually quickly show you. Let me stop sharing my screen on here. It's a little annoying to kind of go back and forth between screens. So this is what it looks like before we do anything in our experiment. So these two ends, they're already thicker than this central kind of region here, just to get a better grip with the jaws that we have for the machine. But the necking that you'd see in the experiment, it's going to occur in here. So basically this cross-sectional area right here, this would be getting smaller in the actual experiment, right in this area. And in one of the pictures we saw, you can actually see that a bit. Oops. Okay, yeah, here. So you see right in here, this cross-sectional area, is smaller than down here and up here. So this is the necking that took place. Okay. Okay. So that's necking, and because of this reduction in this cross-sectional area, the localized stress is going to be increased. Since we were decreasing that cross-sectional area, the stress has to increase. So we can see that. Let's write our formula here. So we have force over area. If our area decreases, then the stress is going to increase. Okay, and because of that, we have this area of localized high stress that's occurring in this center part in here. And because of that, there's higher stress, so eventually we're going to fracture in this area of necking, which we saw in some of the pictures on VKS. And that's when we reach our fracture point up top in our graph here. Okay, let's make one quick note. Necking is only going to occur in a ductile material, not a brittle material. Okay, so a ductile material, that can deform quite a lot. It can have a lot of strain. So because of that, it can undergo a lot of necking. But if we have a brittle material, it might be stronger, but because it's brittle, we can't go or undergo much strain. So because of that, we're not going to see much necking, if any at all. So in our experiment, we'd be applying tension, and visually, you might not be able to see any necking. It would just break. But for something like aluminum, you can actually visually see this necking occur during the lab. So you can visually see that cross-sectional area getting smaller and smaller. Okay, so let's go on here. I don't know why my camera cuts out sometimes. Okay, so fracture. There might be a trick question that some of your instructors or professors ask you guys during class, which is, why is our fracture at a lower stress than anywhere, well, not anywhere else, but why is it at a lower stress than the UTS? So they might ask that in kind of like a tricky way to try to trick you, or see if anyone's like not super smart, but if anyone caught on to them. And basically the answer is that throughout this entire experiment, for these tension tests, we have been assuming that the cross-sectional area was constant. So in our equation, where stress equals force over area, we assume that the area was constant this entire time. But now we know that that's not really the case because we have necking. So really, our stress is increasing the entire time throughout this test. But that's not reflected in our graph here, because we assumed that the cross-sectional area was constant. So why do we assume it's constant? Basically, it's too hard to actually measure that changing area in real time with equipment. I think there is some stuff out there that can measure the changing area during the test, but off the top of my head, I forget, what it's called or how they do it. But the vast majority of tensile tests out there, they don't account for this changing area. And because they don't account for it, that's why we see our stress actually go back down. Because, again, we assumed that the cross-sectional area was constant the entire time. But what it would look like if we were able to keep an eye on the changing area, it would look something like this. So, I don't know, maybe kind of hard to see, but I used dashed lines in gray, so our stress really would increase even after the ultimate tensile stress there. and it would fracture down here. Now, ultimate tensile stress we use for, our typical graph here, but it's, a little different if we are actually counting for this changing cross-sectional area the entire time. But for our sake, we're not going to take a look at this dashed gray line. We're going to keep just looking at this graph that we have on the screen now, which assumes that we have a constant cross-sectional area. Okay, any questions on this? Okay. Okay, we're almost done. We're almost getting there. Again, this is one of the longer lectures that we'll have. There's just a lot of stuff to talk about for the stress strain diagram. Okay, so elastic modulus. Let's talk about that now. Alright, the elastic modulus. So this is going to be a way to characterize a material's behavior within the elastic region. Really, it's used to determine how stiff a material is. So elastic modulus, like the name implies, we need to be within the elastic region. So let's first write down a definition. We're going to say need to be within the elastic region first off. Okay, and this is going to be a way to measure a material's stiffness. Okay, so let's go back up here. So we have our elastic region here, so we need to make sure that if we're looking at the elastic modulus that we're within this blue region down here. So again, it's a way to determine a material stiffness. So actually first I should show you guys the equation that we're going to use, which will be capital E, that's our elastic modulus. Actually, I do it like this. Let's write it out first. So the elastic modulus, that'll be equal to our change in normal strain over the change in normal, it's the change in normal stress over the change in normal strain. So I'm just going to use that delta for change. So change in normal stress over the change in the normal strain. And we can rewrite this as capital E equals delta sigma, which is the change in our stress, over delta epsilon, the change in our strain. So we want to make sure that we're within the elastic region once again. And when we calculate this in our experiment, we're going to compare the calculated elastic modulus that we have, and we're going to compare that to a published value for each material. So to do this, remember it's the change in the normal stress over the change in the normal strain. So we want to go up to the proportional limit, and we want to start from the origin. So by doing this, we can have a wide range for our data, because once we are actually in the lab, well, we're not going to be in the lab, but the data that we get from the lab, it can kind of be a little squiggly. So it's not actually this perfect linear line just because this is the real world. It's not going to be this perfectly linear relationship here. So from these little kind of deflections that we see throughout this elastic range, there's some variability in there. So we want to start from the origin and go up to the proportional limit or just have some decent spread. So we can go, try to, okay, whatever, I'm going to keep that there. So we could use a point like here up to here. We could do that too. Okay, so we would get those two different points. So you would do sigma 2 minus sigma 1 over epsilon 2 minus epsilon 1. And that's how you would find your elastic modulus for the experiment. All right. Okay, so let's go back here. So this is a method again to measure the material stiffness, which gives us a way to predict how much a material is going to stretch, how much it's going to compress or bend under some given load. So this is, if you go in your textbook and you look at some material, the elastic modulus is always going to be one of the things that is given. So let's actually add on right here, predict how much it will stretch or compress. So I'm just going to leave it to stretching or compressing because, sorry, okay, that looks okay. Actually, no, it looks like my screen is cut off a bit. Okay, it's just how I had my zoom set up. Okay, so I'm just going to say stretch or compress for us because that's all we're going to look at for this lab. Actually, not even compressing, so I'll just say predict how much it will stretch. Okay, because we're in tension. Alright, any questions? Alright, so we're on, I think, the last part here, which is ductility. Okay, so the most basic kind of definition for ductility is a material's capacity to have plastic deformation. Okay, so let's go back to my sticky notes. My sticky notes, so they're in equilibrium right now. If I apply a load and deform them, I can bend them. And if I was going to really apply a strong load onto here, I could permanently deform it. So I would have some plastic deformation. So I could permanently deform these sticky notes, but they wouldn't break. They would still, it would be deformed, but nothing would have broke. So because of that, these sticky notes, they are quite ductile. But if I take my iPad pencil here, and I was going to bend this, I would just break it, right? It wouldn't just bend smoothly. At some point, when I'm applying this bending load, I'm not going to actually break it, of course, but at some point, if I kept applying a load, this would just snap in half. It wouldn't have any plastic deformation, because this is a brittle material. Same thing when you drop your phone, of course. It's glass, it's brittle, it's going to break. Of course, wish that didn't happen. But that's the case, right? So if something is really ductile, it can undergo a lot of plastic deformation. It's going to have a lot of strain. If you have a brittle material, it can't withstand much strain at all. So, technically, ductility is not related to strength, but there is, I guess, a kind of a trend. So, oftentimes a brittle material will be stronger than a ductile material. But technically speaking, that's not, set in stone. So they can have the same strength. You can have a brittle material that has the same strength as a ductile material. So you might be thinking, well then why wouldn't you just choose the ductile material? You know, it might be like a cost thing or something like that. But in general, there is a kind of trend again where a brittle material, they're often stronger than ductile materials, but that's not set in stone. So let's add on a few things here. Let's say that a ductile material can withstand a large amount of strain before fracturing. Alright. And the next thing is the brittle material. And that's going to have little to no yielding before fracture. So, said in a different way, it can't have much strain at all before it fractures. Okay, so I think it's kind of intuitive just from your everyday experiences, but just make sure that you keep these things in mind. So I'll also show, I guess, one figure here, which you can find in your Strength of Materials book. Maybe you have a different book than what I used. I think on my book, when I took this class, I had an author called Philpott, something like that. Either way, if it's a different book, you probably have a graph similar to this, where I'll just show you guys where we have different materials, that some are ductile and some are brittle. And even if some are ductile and some are brittle, they can actually have the same stiffness as well. So we have stress and strain. Okay, so here in black, that's a pretty brittle material. And I'll draw one in blue, which will be pretty ductile. So I'll say ductile and brittle. Okay, so one is brittle and one is ductile, but both of these actually have the same stiffness because in their elastic region, they have the same exact slope. So you could see that. I don't think that'll be the case for our experiment, but just something to keep in mind that we could have the same stiffness, but in the end, we could actually have a material that's quite ductile versus a material that's pretty brittle. Okay, so we have two equations that we're going to keep in mind for this first experiment, which will help us determine how ductile a material is. And then that'll be it. Okay. If my writing is ever too shitty and you can't read it, just let me know in the chat, and I'll, point out what I was trying to write. Okay, so we have two measures that we're going to use for this experiment. One of them is going to be called percent elongation, and the other is going to be called percent reduction of area. So again, these are going to be two different methods to measure the ductility of some material. So for this first one, this will be the engineering strain at fracture / percent elongation. So I'm just going to write percent elongation. Okay, so basically what we'd have in our lab we would break our material. So they're going to be in two different separate pieces because it broke. And what we would do is take those two pieces and stick them back together as best we can. And then we would measure our gauge length again. So remember that our gauge length was 2 inches. But what we would do is fit these back together, and we would remeasure the length of our gauge. Well, we'd remeasure the gauge length because it should be longer now because we were necking. Because we were necking, we had to decrease in cross-sectional area, so our specimen was actually elongating. Okay, so we would measure that final gauge length, and then the average strain is going to be calculated from the initial and the final gauge length. Okay, let's actually write this out, and then I'll show you the equation, which really, I think the equation is a better or an easier way to understand this. So let's say step 1, fit broken pieces together. Okay, step 2, measure the final gauge length. Okay, and calculate the average strain from the initial and final gauge length. Okay, and then the actual equation to solve for this is going to be the following. So I'll say, if I say PE, that looks like percent error, so I won't do that. I'll do percent elong, so that's percent elongation, equals LF minus L naught over L naught multiplied by 100. Okay, so this will give us a percent elongation. So LF, that's the final gauge length, and L naught, that's the initial gauge length. Okay, and the second method is percent reduction in cross-sectional area. So off the top of my head, I think we use both methods for this lab, but I know for sure we use percent reduction of area. So as its name implies, we're going to be looking at how much the cross-sectional area has decreased, more specifically in the gauge length where we had the necking take place. So percent reduction in area say PRA, percent reduction of area, that's going to be equal to A naught minus AF over A naught, and then multiply it by 100 to get a percentage. Okay, so A naught, that's going to be the original cross-sectional area, and AF will be the cross-sectional area at fracture. Okay, so I know for sure we're using percent reduction area, and I think we're doing percent elongation as well, but off of the top of my head I can't remember, but make sure you have both of these equations written down because you're going to be using them for the lab. So before we leave, I'm going to stop sharing my screen. So if you didn't get everything here, I'm going to upload the lecture, remember that. But I want to show you what this would look like before we leave today. So, yeah. They don't, they almost make it seem like this was after the fracture, but I think this is before. So here, this is at fracture, right? So what you would do for this stuff is you would take both of these ends and you would kind of fit them together as best as you could. And so for the first thing, we measured the gauge length. In the beginning, that was 2 inches. That's the default length here with the extensometer. And then you would get the gauge length that we had in the end. So basically just how much it deformed. So then you could calculate the percent elongation. And then as for the percent reduction in area, you would have had measurements of this area in the beginning of the lab before you started. And then you would fit these two pieces together as best you could. And then you would measure this cross-sectional area at this point where we had the fracture. And then you would plug that into the equations that we have, and you could find a way to measure the ductility for these 3 different materials. So for aluminum, there would be a lot of necking that can occur, so the cross-sectional area would decrease more because it's a more ductile material. And then for steel, it wouldn't decrease as much because it's not quite as ductile as aluminum. Okay, so basically that's just a method to determine the ductility of these materials. Alright, any questions before we finish today? Alright, so that's it for the lecture. Next week we're going to have our, pseudo experiment. I'll give you more info before we actually start because I still need to figure out exactly how I want to go about it. We'll go over this, I think, as a class. Everything on VKS here. I'll probably have you watch a video as well. And at some point, we're going to be going over some stuff in MATLAB as well. I don't know if I'll do that next week or not. I'm not totally sure on that quite yet. But I'll let you guys know. So don't worry about that. So if you don't have any questions, that's all I have for you guys today. So I'll see you next week. But if you have any questions, then I'll stick around for a bit. Alright, so have a good week, guys.
Thanks, Professor.
Thank you.
Mhm.
Thank you.
Mm-hmm.